Okay, let's talk about surface area, and we're going to find the surface area of shapes that we actually revolve around an axis. So similar to some of the volume and arc length stuff we've done. So let's look at just a nice easy curve. And I'm not the best at drawing these, but let's look at y equals x squared, which is our nice parabola, right? Something like that. And then let's revolve this around the x-axis. Let's revolve it around the x-axis, okay, and that's going to form that tornado kind of shape. Okay, something that looks like that. So it's not a cone, because this is some curve, but it kind of looks like a cone, or I always call them a tornado. So we want to find the surface area of that thing. And it turns out that we're going to take this and we're going to view this. Right? Think of that red as having a little bitty thickness. Okay? And so then the surface area of that tornado should be the summation of all of the rings. Again, we use calculus to do all that, do that all the time. So the surface area is we need to sum up all the different DAs of the rings. Okay, and then so what is then the surface area of each ring? Okay, so the surface area of each ring, if you think about that for a second, each ring, if you kind of slice it and unravel it, it's going to have this curved part here, something that kind of looks like this, and then a curved kind of part down there, okay? Something that kind of looks like that. Okay, so this distance is 2 pi r. And this distance is what? Well, this distance is the length along the arc that we traveled for that, right? It's the length of the ring this way times the thickness of the ring, but the thickness of the ring is going back to the arc length formula. The thickness of the ring is actually 1 plus dy dx squared dx. And again, we decided this in the last video or last unit, that the arc length formula, which is derived from the Pythagorean theorem, it's actually not difficult at all to show that the length of some curve is this guy, okay? And so when we're looking for the length of the curve, this length is looking at this piece right here. That dimension is the arc length of this curve. And then this is just 2 pi r, where r is the height here. Okay? So if we look at this, we need to do 2 pi r times the thickness. So we need to do 2 pi. R in this case is just x squared, right? This distance right here is our r value, and our r value is our y value. And in this particular case, y equals x squared. So 2 pi r, and then times 1 plus dy dx, which in this case is 2x squared dx. So the surface area of this particular cone, again, it's the summation of all of these DAs. DA is the surface area of each ring. And if you sum up all the areas of the ring, then you get the surface area of the tornado. Each ring is its own surface area, right? The surface area of each ring is this guy. Well, that guy has this as, think of it as a rectangle. This length is the arc length formula, which we derived. And then this length is just 2 pi r, because if you slice this and you unravel this, this distance is just the circumference of that ring. Okay, and so then we've derived our surface area formula. The surface area formula, really in the abstract, is going to be the accumulation of 2 pi r times 1 plus dy dx squared dx. Okay, and so if you do that, for this particular one, if you continue to do this curve, and let's say this was bounded, I don't know, between 0 and 3, when you type this in, you're going to get 261.32, and that could be in like square inches, right? Square feet, square inches, square whatever, because it's an area, it's a surface area. Okay? So let's do something different. Let's do another example. Let's do y equals the cube root of x, which is kind of going to be an upward tornado looking thing. So it looks something like this. Okay, this is the point 8, 2, and let's revolve it around this axis. So kind of an upward tornado. And you got to think about how that's going to work. Again, you're going to take this and you're going to sum up a bunch of those kind of rings. So you're stacking them vertically. So hopefully you understand that this formula is symmetric. In this case, say we did the x, and here we're going to do y. So we're going to do the integral of 2 pi r. Now what is r in this case? Well, r is this distance. Right, here's the radius of that ring. This distance is x equals y cubed. Okay, so 2 pi r, in this case r is y cubed, times the square root of 1 plus, and we're in y, so we can't do dy dx, we need to do dx dy. So dx dy is actually 3y squared. So 3y squared dy, and we're going to integrate from 0, not 0 to 8, but 0 to 2. So we're going to stack these rings from 0 to 2, and the area of all the summation of the area of all the rings is then the area of our tornado. In this case, it's a vertical one, 0.04, and let's say we're in cube or square centimeters or something. Okay, it's kind of an idea makes sense. Again, it's really just a piggybacking on the fact that we know that we can find the length of a curve, and we know that area is just the surface area in this case is the area of this three-dimensional object on the outside. And I guess I want to point out that we're not including, this. We're not including this guy, which is just a circle. We're just talking about, I guess, the lateral surface area. Again, over here, we're not talking about this. We're only talking about kind of the wall of the tornado. If we wanted to add this, well, that is just a circle in this case. This was we had x equals to 3, so this was the 0.3, 9. So if we wanted to add this, this is just pi times 9 squared. So that is just 81 pi if we wanted to add that onto there to actually get the total surface area of, painting that whole thing or something. Okay, and I guess I want to go over one more thing, not a different real question, but just an idea of, back in geometry, you memorized something about a cone, okay? So you decided that cones had lateral surface area that were equal to pi r L. It's something you either memorized or maybe your teacher showed it to you. Okay, L is this slant height of the cone, and then that, of course, is the radius of the cone. And you memorize that the lateral surface area, the wall here, is this, and I just want to prove that that is actually the case. Okay, so let's take something, and let's take the line y equals to 2x, okay, y equals 2x, and let's revolve it. And in this case, we actually do get a cone, right? We don't get a tornado, we get a cone because we're taking a line. So this is the point 4 comma 8, and then we're going to revolve it. So if we use the calculus formula that we derived, we would say that the surface area is the accumulation, and again we're accumulating these rings, right? Give it a little thickness. Okay, accumulating these rings this way, we're going to accumulate them from 0 to an x value of 4. We're going to go 2 pi r. R is this distance, which is 2x in this particular case, times the square root of 1 plus the derivative squared, which is just 2 squared, dx. Okay, well, all of this actually simplifies pretty easy. This is a 2 and a 2, and this is just the square root of 5. So this is 4 square root of 5, 4 square root of 5 pi, and the only thing left in the integral is x. You can certainly do that by hand. So this is 4 radical 5 pi, and then this is going to be x squared over 2 evaluated from 0 to 4. Okay, so then that's 16 over 2, which is 8, 8 and 4, so this is 32 radical 5 pi. That's what I claim the surface area is by doing the calculus, and the calculus says that I'm going to sum up all of these rings. Each ring is its circumference times the length of each ring, and again the length of each ring is the arc length of that particular curve. Okay, so now let's do the geometry of this, right? This cone is kind of sideways. This cone that I drew is kind of not sideways. Let's maybe make that a little bit bigger and we can decide what all these things are. Okay, so this cone has a radius of 8, right? That distance is 8. Okay, so we know the radius of our cone is 8. The height of our cone is this distance, which is 4. This cone is a awful, couldn't be probably worse in terms of the scale, considering that's 4 and that's supposed to be 8. So it's supposed to be a much fatter cone like this is than a skinny cone, but that's okay. The slant height then is truly the Pythagorean theorem of those things. So this slant height of the cone is 4 squared plus 8 squared equals L squared. 16 plus 64 equals L squared. So that's the square root of 80 equals L. What is that? That's 16. That's 16 times 5. 16 times 5. So that's 4 radical 5 is L. And then our geometry formula that you believed your geometry teachers is pi r L. And you can see that your geometry teacher wasn't lying to you, nor am I, and that the calculus derivation of the surface area of a cone and the geometry formula you memorize indeed do give you the same result, which is kind of cool. Okay, so surface area is not too bad. Again, the surface area formula does rely on the fact that you understand how the arc length formula came, because we do need the arc length of that particular little curved segment. But really all we're doing is the same thing we always do in calculus. We're breaking it up into pieces. In this case, we're breaking it up into rings. The total surface area is just the surface area of each ring, and then sum them up. And then so this is kind of the formula. And again, I did show you an X version and a Y version to show you that these two formulas are kind of symmetric. Okay, so that's surface area.